Video we discuss about the Verilog code for the ripple carry adder. So here in this video the ripple carry adder we are going to discuss how you design the ripple carry adder. So you all know about how the ripple carry adder is like. It is like by using half adder we just add 2 bits, and by using full adder we use 3 bits. 1 2 means it is a 1 bit, it is 1 bit, it is 1 bit. So you can add 3 bits. While in half adder we simply add 2 bits. So like that. So but by using these ripple carry adder, at a time we can add multiple means every single if A is a one character, if you design it is a 4-bit number, and B is another character, it is like 1 0 1 0 like that. So at a time we can add 2 numbers by using this ripple carry adder. So for this purpose we are going to use full adders. So now you are getting some doubt. So why you use only full adder? Why not half adder like that? Because there is only 2 bits. For adding 2 bits the half adder is enough. But why you use full adder only? Why not half adder? Means there is a one problem. So if it is 1 0, that is nothing but 1. So 1 plus 1. So you get 0 carry with 1. So now here observe, there is a chance of getting 3 bits while you are doing or performing any addition operation here. So that's why we need to we don't know whether it is a full adder or half adder. We can't check every time. So that's why for our convenience we have to use the full adders. So maybe the chance of getting carry like this, so on that time we have to choose full adder. So that's why we are going to full adder instead of half adder. So now see module full adder. So for that first we have to write full adder code, then we have to instance this full adder code in our carry ripple adder code. So how is our carry ripple adder look like means, so it is like this. So it has 4 full adders. For how many bits we take, so that number of full adders we need. So full adder 4, so it is 1 2 3 like that. So how many inputs we are giving? A and B. So initially we give the Cn as 0. So initially we don't have any carry, so that's why we can give Cn as 0. So what is our outputs? So sum and carry is our output. So we get sum and then carry. So again these for the 2 inputs again. So for every full adder there is a 3 inputs. So what is the third input? So what is the carry generated by the first full adder is given to the second one. Again sum, the carry is given to the third full adder. So again it is a sum, the carry is given to the fourth full adder. Then finally we get a sum and the carry. So like that it is our ripple carry adder. So let's see. So for that we have to write the full adder code. We already discussed this full adder code. Simply write module and end module. So full adder is our module name. So what are the input ports for the full adder? A, B, C. For it is a full adder. So A, B, C are the inputs and sum and carry are our outputs. A, B, C, and it is our carry and it is our sum. So for that for representing input ports we are simply write input A, B, C. So for output sum, carry. So by using data flow model you are assigning here. So how you can assign? So by using assign keyword you have to assign the RHS value to LHS. For sum, what is the formula? AX or BX or C. For sum, AX or BX or C. So in Verilog the XOR symbol is like cap symbol. So for carry, what is the formula? AB plus BC plus CA. So end operation is represented by ampersand. So whereas OR operation is represented by A symbol. So here you can convert this formula and assign those value to carry by using this assign keyword. It is our full adder code. So we have to instance this full adder code in our ripple carry adder code. So how you are going to assign means, so see. So first you have to write separate code for ripple carry adder. So it is our module and end module. So inside that we have to going to write the code of ripple carry adder. So ripple carry adder is our module name. So what are the inputs here we can observe? So there are the, for a variable there are the 4 inputs. So now we are going to assign a vector format. So we all here 4 bits. So 0 index 1 2 3. So it is our index number. So 0 to 3. So here 3:0 represent like that, comma 3:0 of B means A and B are the 4-bit values. So its size will be 4 bit. So and input Cn. So Cn initially we are going to give it is a 0. So Cn is input 0. So whereas output, so how many bits you are getting? Sum also 4 bit and extra you get carry. So for that 4 bit we sum, we can represent it like this and the output will be the carry. So for reg, why I use this reg means, so in middle of the full adders you can observe the carry is given to the second full adder and second full adder carry is given to third full adder, like that. So no need to store these all values. These are not input ports and output ports. So these are just giving values, means drive the values from one port to another port. So output of first full adder to input for the second full adder, like that we are going to drive, not we are going to any storage purpose. We are going to store, means whatever the value you get, so you have to store that, or you can simply give that value to the second full adder. So for that purpose we are using reg data type or wide data type. You can use anything, but for my convenience I use reg here. So no need to particularly mention reg. You can use wire also, means net data type also. So by that there is not an input port, output port. We just simply connect those ports for our convenience. So that's why I represented reg. So how many carries we generated? Full adder 1 carry, 2, 3. So for 3 only. So for 4 is our final carry. So no need to mention these carries. So only 3 means 2 is to 0. 2, 1, 0. So it is our index number. So 3. So 3 bit number. So how you are going to instance it? You are know that. So what you are going to instance? So write that instance module name. So you have to instance the full adder code in the ripple carry adder code. So we can write the module name. So what you want to instance? So write that module name. I want to instance the full adder code. So that's why I write full adder, full underscore adder. It is our module name. So Teju is our instance name. So you can write any name. No need to particularly mention same thing, but it not should be a keyword. So no need to, means here we don't write the same instance name to everything. So if you write like that means it shows duplicate one. So you can take separate instance name. No need to it is a specific name. So it not should be a keyword in Verilog. So how you connect these ports? So what are the inputs? So A, B. So A of 0 and B of 0 and the C. So first full adder we can see that A, B. So what is the index number? 0. So A of 0, B of 0 and C. So what you get? Sum. So index number will be 0. So carry will be the C of 0. So again second full adder inputs are A of 1 and the B of 1. So what is our third input? So C of 0 are going drive to input to the second one. So that's why you simply write C of 0 and the sum carry. Like that we can instant every line. So finally you get carry and the sum. So sum is nothing but these 4 bits. So sum of 0, sum of, so it will be simply assigned. So final carry is our carry. So you can stop with 10 module. So it is our design code. So next we are looking into the test bench code. So here also test bench code is start with module and end with end module. So you have to write the module name here. So carry underscore ripple underscore adder underscore TB is nothing but our module name. So input ports are represented with reg data type. So wire is represented means it is output ports are represented in wide data type. So what are the variables we are using in the initial block? It must should be in the reg data type only. So that's why I represented input ports with reg data type. So otherwise you can represent input ports as netted data type also. But why particularly reg means because of initial block. So what are the variables we are used in the initial block? It must should be only reg data type. So for our next process is our ripple carrier. So you have to instance the design code in the test bench code. So for that we have to write the module name here. So ripple underscore carry underscore is our module name in here. So Teji is our instance name. So you can write any instance name every time we discuss about that. So it is our port connection. So you simply connect the ports what you want. So input ports and the test bench ports are be connected properly by order here. So here we connected by order. So in initial block we already discussed that test bench code is similar to every program. So first we have to write the module and end module. You can write module name and inputs are in reg data type, output are in wide data type. And we have to instance the design code in test bench code, then initial block and then 4 lines for the waveforms. So this is the same format. So just remember the syntax and change the module names and what are the inputs, what are the port connections, what is our module name in design code. Just you have to instance. These are the modifications. Otherwise the remaining everything is same. So initial block what you are only we can assign only the input. What are the inputs we consider ABC or inputs. So you can take different combinations for the input ports and we get observe the outputs in waveform like that. So here I take the ABC values differently and I can observe in waveform. So that's why in EDA playground if you want to generate the waveform, so you can write this 4 lines simply and stop with N1. So finally it is our output like that. So you can double click on this scale, then you can represent those values here. So C. A is equal to 4 and B is equal to 5. So in Cin, Cin is our third input, so it is 1. So how we are going to represent? So we can represent this by 4 bits. Because why? Because here we can observe there is a 3:0. 3:0 means it is a 4 bit. 3, 2, 1, 0. So 1, 2. So it is our index number. So we can represent it by 4 bits. So 1, 0, 0 and 5 is represented like this. So Cin means 0, 0, 0, 1. So here we get 0, 1 and then 0 carry with 1, 1. So 1, 0, 1, 0. 1, 0, 1, 0 is nothing but we have to convert this into the decimal format. So there is no carry generation here. So there is no carry generation. That's why the carry will be 0 here. The output will be represented by A. So you can convert this hexadecimal format to binary format. So how we are going to 1, 2, 4, 8. So it is our, so it will be 0 plus, so 2 into 1 is 2, 0 plus 8 into 1, 8. So that is our 10. So in decimal we can represent 10 by A. So simply write A here. Sorry, hexadecimal you can simply represent it by A. So you can simply represent it by A. So here the it can be represented in hexadecimal format. So just remember, if you don't mention anything like 4 tick B, 0, 0, 1 like that, or 3 tick H like that, you don't mention any particular HB, it defaultly take it is a hexadecimal number. So that's why it will consider like this. So till then it is our ripple carry adder Verilog code. If you have any doubts, you can comment it in that any single line. If you have get error or if you confusion, then you can comment it also. I will make sure that I will separately explain that particular single line or single data type also. So no need to hesitate to ask any questions in comment section. So thanks for watching. Until then, bye.